In the preceding chapters, we studied how one of the properties of solids was rigidity. We studied that solids had a definite shape and size. However, this is true for only ideal solids. In real life, it is possible to modify the shape, size, and volume of a solid by applying force on it. Let us begin by studying a spring. If we pull the ends of a spring, we find that we can increase its length by a certain amount. Releasing it, however, returns it back to its original shape and size. Similarly, you may press the ends of a spring together to decrease its length. But upon releasing the pressure, the spring returns to how it was before. This property of a body to return to its original shape and size as soon as the pressure applied on it is removed is known as elasticity. The deformation caused on solids when pressure is applied on them is known as elastic deformation. There are other substances like mud which do not behave in this way. Let us take a lump of clay. In the conventional sense, this lump is a solid. However, when you apply pressure on it, the clay changes shape and flattens out. Moreover, when you take your hand off the lump, it still remains flattened. Thus, there are some solids which deform under application of pressure, and do not regain their original shape and size after the pressure is removed. Such solids are known as plastics. Their deformation is known as plastic deformation. For engineers designing high-load structures like buildings, bridges, aeroplanes, etc., the study of these properties of solids is of extreme importance. Behavior of solids. We know that solids are made up of closely packed atoms and molecules. These atoms are held together by interatomic and intermolecular forces, which keep them together in a stable position. Deformation of solids leads to a change in the interatomic or intermolecular distances. However, when the applied force is removed, the intermolecular or interatomic forces tend to drive the atoms and molecules back to their original position. This makes the solid return back to its original shape and size. This restoring force is easy to visualize with the help of what is known as the spring ball model. The balls represent the atoms, and the springs are analogous to interatomic forces. Let us displace one of the balls on the surface from its position. We see that disturbing any of the balls from the equilibrium position leads to the other balls being affected as well. But releasing this ball results in its returning to its original position. The entire model regains its original shape and size too. Elastic nature of a solid, therefore, is due to its microscopic properties. Robert Hooke performed several experiments on springs and discovered that change in length of a solid was proportional to the force or load applied on it. This is what we now know as Hooke's law. Hooke's law is of extreme significance when we design load-bearing structures. And strain. Deformation of a body due to the application of a force on it may be small or large in magnitude, depending on the amount of force applied. When a solid is subject to a deforming force, a restoring force develops in the solid to counter it. This restoring force is equal to the deforming force in magnitude, but is opposite in direction to it. Restoring force developed in the solid per unit area is known as stress. Thus, if the force applied on an area of cross-section A is F, then magnitude of stress equals F by A. The SI unit of stress is Newton per meter square. Pascal, PA, may also be used as a unit. Stress has the dimensional formula mL raised to minus 1T raised to minus 2. A solid may get deformed due to an external force in three different ways. When a solid is deformed by the application of forces normal to its cross-sectional area, such that it is compressed, then the force is known as compressive stress. Similarly, if such a force acts to expand the solid, then the restoring force per unit area is known as tensile stress. Both these forces taken together can be generalized as longitudinal stress. Longitudinal stress results in change in length of the cylinder. The ratio of change in length of the solid to the original length is known as longitudinal strain. If two equal and opposite deforming forces are applied parallel to the cross-sectional area of the solid, then the opposite faces of the solid undergo relative displacement. This deformation, occurring due to the application of tangential forces on the solid, is known as tangential or shearing stress. The strain caused due to the relative displacement delta x between the opposing faces of the solid is known as shearing strain. It is defined as the ratio between the relative displacement of the faces delta x and the length of the solid L. Shearing strain equals delta x by L equals tan theta. Here, theta is the angular displacement of the solid from its original position. When a solid is placed inside a fluid, it is compressed from all sides. At each point on the surface of the solid, the pressure acting is perpendicular to the surface of the solid. This is known as hydraulic compression. In response to this compression, the body develops restoring forces within itself. This internal restoring force per unit area is known as hydraulic stress. It is equal to the hydraulic pressure on the solid in magnitude. Strain produced in case of hydraulic stress is defined as the ratio of the change in volume as compared to the original volume. It is known as volume strain. Strain is a ratio of change of the same quantity with respect to itself, and hence has no unit or dimensional form. Stress-strain curve. For finding out the relationship between stress and strain for a material under tensile stress, we generally use a test cylinder and stretch it by applying a force. Changes in length are observed to measure the strain, which is then plotted with respect to the stress. Stress-strain curves differ with different materials used as the test cylinder. Graphs for compression and shear stress are analogous to those for tensile stress. Let us now study one such curve in detail. Between points 0 and A, the curve is a straight line. Hooke's law is obeyed in this region. This region is the region of elastic behavior. In this region, application of a force deforms the body, but removal of the force results in the body returning to its original form. Stress and strain are not proportional in the region AB, but the body still returns to its original position on removal of force within the region. The point B is known as the yield point. The stress at point B is known as the yield strength. Application of stress greater than the yield stress leads to a rapid increase in strain. This is shown in the region BD. In this region, the material ceases to exhibit elastic behavior and becomes plastic in nature. This means that the material cannot recover completely from the applied force and remains deformed. Thus, even though stress may be zero, strain is not zero. The material is then said to have a permanent set. The deformation in this case is known as plastic deformation. The point D is known as the ultimate tensile strength of the material. Beyond this point, applying even a lesser force will result in additional strain in the material. If the points C and D are close to each other, then the material is brittle in nature. If these 2 points are at a distance from each other, then the material is ductile. Materials like rubber can be stretched over long lengths and still manage to return to their original shape. These materials are characterized by a large elastic region, although the entire region may not obey Hooke's law. Such materials are known as elastomers. Hooke's law. As we saw in the previous section, stress and strain can take up various forms. For deformations which are small in nature, stress and strain are proportional to each other. This is known as Hooke's law. Thus, stress is proportional to strain, or stress equals K into strain. K is a proportionality constant known as the modulus of elasticity. Hooke's law is empirical in nature, and although most materials exhibit it, there are some materials which do not follow this law. Thomas Young demonstrated experimentally that magnitude of strain produced is the same for the stress being tensile or compressive. The ratio of stress sigma to the longitudinal strain epsilon is thus defined as Young's modulus. Young's modulus is represented by Y. Y equals sigma by epsilon. This can be written as Y equals F by A by delta L by L, which equals F into L by A into delta L. Strain is a dimensionless quantity, and hence the unit of Young's modulus is the same as that of stress, that is, Pascal. Metals usually have a large value of Young's modulus. This can be seen from the table given. This is the reason why most heavy-duty applications make use of metals. Determination of Young's modulus for the material of a wire. In the last section, we defined the meaning and relevance of Young's modulus. Let us now learn how to experimentally determine Young's modulus. We take two wires, A and B. Both these wires are made of the same material, have the same cross-sectional area, and have the same length. The wire A carries on it a millimeter scale and is known as the control wire or the reference wire. It also carries at its end a known weight, which is used to keep the wire taut. Wire B is known as the experimental wire. It is attached to a vernier scale, which rests next to the millimeter scale, and has provision at its end to add weights. Adding weights to the experimental wire causes it to stretch under the downwards acting force of the weights. The reference wire compensates for any changes in the length of the wire due to temperature changes, since both wired would be equally affected. Initially, after the wires are loaded, the vernier reading is noted. The experimental wire is then loaded with more weights, leading to tensile stress in the wire. The vernier reading is then noted again. Weights are then added again to the experimental wire, adding to the stress, after which vernier reading are noted again. Elongation of the wire is given by the difference in the vernier readings as weights are added. Let the initial radius of the wire be r, and the initial length of the experimental wire be L. The area of cross-section of the wire, thus, is pi r square. Let delta L be the elongation produced in the wire due to the mass m. The force applied on the wire equals mg, where g is the acceleration due to gravity. The Young's modulus of the wire B is then given by Y equals sigma by epsilon equals mg by pi r square into L by delta L, which equals mg into L by pi r square into delta L. Shear modulus. Shear modulus of a material is the ratio of the shearing stress to shearing strain of the material. Shear modulus is represented by G. It is also known as the modulus of rigidity. G equals shearing stress by shearing strain, which equals F by A by delta X by L, which equals F into L by A into delta X.
We know that shearing strain is equal to tan theta equals theta.
Therefore, G equals F by A by theta, which is equal to F by A into theta.
The shearing stress sigma S can also be expressed as sigma S equals G into theta.
Shear modulus has the SI unit Newton per square meter, or Pascal. For most materials, the shear modulus G is almost equal to Y by 3. The table here shows the shear modulus for some common materials. Bulk modulus. We studied in earlier sections how submerging a body in fluid leads to it experiencing hydraulic stress. Hydraulic stress leads to a decrease in the volume of the body, and also leads to strain, which is known as volume strain. Bulk modulus is the ratio of hydraulic stress to the corresponding hydraulic strain. Bulk modulus is represented by the symbol B. B is equal to minus P whole divided by delta V by V. The negative sign indicates that as pressure increases, the volume decreases. Thus, when P is positive, delta V has a negative value. For a system in equilibrium, bulk modulus B always has a positive value. The SI unit of bulk modulus is the same as that of pressure, N per meter square or Pascal. The table here shows the bulk modulus of some common material. Compressibility, K, is the reciprocal of bulk modulus. Compressibility is defined as the fractional change in volume per unit change in pressure. K is equal to 1 by B, which is equal to minus 1 by delta P into delta V by V. From the table for bulk moduli, it is clear that the bulk moduli for solids is much larger than that for liquids, which is again much larger than that of gases. This means that solids are the least compressible of all materials, while gases are the most compressible. In fact, gases are about 1,000,000 times more compressible than solids. Solids are incompressible by virtue of their tight molecular structure. Liquids are more loosely bound, which gives them a degree of compressibility, while gases are the least tightly bound, making them extremely compressible. Applications of elastic behavior of materials. At the beginning of this chapter, we mentioned how the study of the mechanical properties of solids is extremely important for engineers designing heavy-duty, load-bearing structures. For example, when designing a building, it is extremely important for the engineer designing it to know the elastic properties of the materials that will be used to fabricate the columns, supports, and beams. Let us try to design a crane to carry a certain load for us. For a crane to lift an object, the object first has to be attached to a thick metal wire. This metal wire is then pulled up by means of pulleys and motors. Suppose we need to lift a 10 metric ton load. When lifting this load, it is important that the metal wire not deform or fracture. The stress on the wire thus must be in the elastic region, and the extension of the wire due to the load must not extend beyond the elastic limit. Let us use mild steel to design this wire. We know that mild steel has a yield strength psi of 300 into 106 Newton per square meter. The area of cross-section of the wire therefore must be at least A greater than or equal to W by psi, which is equal to mg by psi. This is further equal to 10 to the power 4 kilograms into 10 meter per second square whole divided by 300 into 10 to the power 6 Newton per meter square. This is finally equal to 3.3 into 10 to the power minus 4 meter square. This is equivalent to a wire of circular cross-section with radius of 1 comfort. For the sake of safety, radius of the wire used is usually much larger than that obtained mathematically. Thus, we would probably use a wire with radius 3 centimeters instead of the 1 centimeter that we obtained. Since wire this thick would actually be a steel rod, we use wire made up of a large number of wires of smaller radii braided together. This eases manufacture of the wire while giving it greater strength and flexibility. Bridges and buildings involve structures which need to support extremely high loads. When designing such structures, it is important to ensure that application of a load does not lead to the bending of the support beams. Let us look at a beam loaded at the center and supported at the ends. A beam with length L, breadth B, and depth D, when loaded with a weight W at the center, sags by an amount delta equal to WL cube whole divided by 4BD cube Y. In order to reduce the bending of the beam, it is important that we use a material which has a large value of Young's modulus Y. Also, since the sag is inversely proportional to the cube of depth and the breadth of the beam, increasing the depth is more effective in reducing the sag of the material. The deep bar, however, may buckle if the load is not at the right place. This is difficult to achieve when we consider a bridge which has moving traffic on it. To prevent buckling, load-bearing beams are designed with an L-shaped cross-section. Pillars and columns in buildings and bridges are also built with distributed ends, so that they can support a greater load without compromising their structural integrity. The tallest mountain in the world, Mount Everest, has a height of 8.84 kilometers. But can there be a mountain taller than the Everest? And can mountains be infinitely tall? Let us find out. The base of a mountain is not under uniform compression. This provides some shearing stress to the rocks below, causing them to flow. For a mountain to exist in a stable fashion, the stress due to the combined weight of everything on top of the mountain should be less than the critical shearing stress of the rocks forming the base of the mountain. Let the height of the mountain be h.
The force per unit of a mountain is
H rho g.
here
Rho
is density of the material which makes up the mountain, and g is the acceleration due to gravity.
the shear force acting on the base of the mountain equal h rho g itself. Since for a typical rock the elastic limit is 30 into 10 to the power 7 Newton per meter square, the value of h rho g is equal to 30 into 10 to the power 7 Newton per meter square, or h is equal to 30 into 10 to the power 7 Newton per meter square, whole divided by 3 into 10 to the power 3 kilogram per meter cube into 10 meter per second square. This is equal to 10 kilometers. Therefore, the maximum possible height that a mountain can have is 10 kilometers, which is 1.2 kilometers greater than Mount Everest.
Can be rolled along its length. The length L and the radius R of the rod are 2.25 meters and 5 millimeters respectively. A force of 125 kilonewtons stretches it along its length. Find out stress, elongation, and strain on the rod. Given Young's modulus of steel is 2 into 10 raised to 11 newtons per square meter. Solution. Considering the structure of the bridge, we assume that the force experienced by the rod is parallel to its length and applied to one of the ends, whereas the other end is fixed in space. Thus, the stress on the rod equals F by A equals F by pi r square equals 125 into 10 raised to 3 by pi into 5 into 10 raised to minus 3 whole square equals 5 by pi into 10 raised to 9 newtons per square meter. The net change in elongation, that is delta L, equals F by A into L by Y, or delta L equals 5 by pi into 10 raised to 9 into 2.25 by 2 into 10 raised to 11 equals 1.791 into 10 raised to minus 2 meters equals 1.79 centimeters. Thus, strain equals delta L by L equals 1.79 into 10 raised to minus 2 meters by 2.25, approximately equal to 0.8%. Example 9.2. Two dissimilar wires made up of wrought iron and aluminium are joined end to end. They have the same radius R of 6 millimeters, but their lengths are L, Wi, and 2.4 meters and La equals 1.8 meters respectively. Obtain the load applied on this combination if the net elongation found after the application of this load was 0.66 millimeters. Given Ya equals 70 into 10 raised to 9 newtons per meter square. Ywi equals 190 into 10 raised to 9 newtons per meter square. Solution. From the given problem, we can conclude that both the wires experience the same force in the form of a tensile stress, as because they have the same cross-sectional area and the same load, let the load be ml. Stress equals F by A equals ml by pi r square. Also, stress equals delta L by L into Y. Hence, ml by pi r square equals delta La by La into Ya equals delta Lwi by Lwi into Ywi, or delta La by 1.8 into 70 into 10 raised to 9 equals delta Lwi by 2.4 into 190 into 10 raised to 9, or delta LA by delta LWI equals 1.8 by 2.4 into 190 by 70 equals 3 by 4 into 19 by 7 equals 2.035. Also given that delta LA plus delta LWI equals 0.66 millimeters. As delta LA equals 2.035 into delta LWI, delta LWI into 1 plus 2.035 equals 0.66 millimeters, or delta LWI equals 0.66 by 3.035 millimeters equals 0.2174 millimeters. Hence, delta LA equals 2.035 into 0.2174 millimeters equals 0.4424 millimeters. Now, to calculate the velocity of ml, we have ml by pi into 6 into 10 raised to minus 3 whole square equals 0.4424 into 10 raised to minus 3 into 70 into 10 raised to 9 by 1.8, or ml equals 0.4424 into 10 raised to minus 3 into 70 into 36 into 22 by 1.8 into 7 equals 194.656 newtons.
Example 9.3. The given figure shows a traditional dance in Indonesia. The entire weight of the performer A, who is on top, is supported by another performer B, who is lying on her back. The net weight of the entire arrangement, along with all the objects used for the performance, is 125 kgs, and the mass of performer B is 55 kgs. The length of the thigh bone of performer B is L, 45 centimeters in length, and has a radius r of 2.25 centimeters. Calculate the compression in her thigh bone, assuming the load is uniform all throughout. Given y bone equals 9.4 into 10 raised to 9 Newton per meter square. Solution. The net mass of the entire arrangement equals 125 kgs. The mass of performer B equals 55 kgs. Hence, the total mass supported by performer B on her single thigh bone is 125 minus 55, which equals 70 kgs. Hence, weight of the supported mass equals 70 into 9.8 newtons, which equals 686 newtons. This will be the total load, M load, for the purpose of calculation. Now, the cross-sectional area of the thigh bone is A equals pi r square equals pi into 2.25 into 10 raised to minus 2 whole square meter square. Now, we know that delta L by L equals F by A by Y. Or in this case, as F equals M load, Y equals Y bone, delta L equals L into M load by A into Y bone, which equals 45 into 10 raised to minus 2 into 686 by pi into 2.25 into 10 raised to minus 2 whole square into 9.4 into 10 raised to 9 equals 2.06 into 10 raised to minus 5 meters. Also, the fractional decrease in the length equals delta L by L, which equals 2.06 into 10 raised to minus 5 by 45 into 10 raised to minus 2 equals 4.57 into 10 raised to minus 5 equals 0.00457%.
Example 9.4. A square steel suitcase is riveted to the floor for testing the endurance of the product. The side S is of 36 centimeters and the thickness T is 12 centimeters. On the application of a shearing force Fs of magnitude 6.6 into 10 raised to 4 newtons on the narrow face, the upper edge was displaced by delta y meters. Calculate delta y. Given Gs equals 84 into 10 raised to 9 newtons per meter square. Solution. The force is parallel to the face PQRS. Area of PQRS of A equals S into T equals 36 into 12 centimeters square equals 432 centimeters square equals 0.0432 meters square. Hence, stress equals Fs by A equals 6.6 into 10 raised to 4 by 0.0432 newtons per square meter equals 1.52 into 10 raised to 6 newtons per square meter. We also know that shearing strain equals stress by Gs equals delta y by S. Therefore, the net displacement parallel to the PQRS plane equals delta y is delta y equals S into stress by Gs 0.36 into 1.52 into 10 raised to 6 by 84 into 10 raised to 9 meters equals 0.0065 into 10 raised to minus 3 meters. Example 9.5. The Pacific Ocean has an average depth of 4.2 kilometers. It is also given that the fractional compression delta V by V, as calculated by the National Geographic team at the bottom of the ocean, is X%. Find out the value of X. Given that bulk modulus of water, BW, equals 2.2 into 10 raised to 9 newtons per meter square, density of water, rho, equals 1000 kilograms per meter cube. Solution. Firstly, we calculate the pressure experienced in the ocean bed, which is at a depth of 4.2 kilometers, equals 4,200 meters. P water equals H rho G equals 4,200 into 1,000 into 9.8 equals 4.11 into 10 raised to 7 newtons per meter square. Hence, P water will be the stress experienced at the ocean bed. Now we know that delta V by V equals stress by BW equals 4.11 into 10 raised to 7 by 2.2 into 10 raised to 9 equals 1.868 into 10 raised to minus 2 equals 1.868%. Hence, the value of X